Roman numeral problem, right? The basic idea is we're given a number and we need to translate it into Roman numerals, right? And this was like the boss level one, was this number of 1994, and let's translate it into this number, right? And remember, like, from last class, the general idea was, well, this is kind of like the small change problem, meaning that if we have this amount, like 11, start with the largest, like denominations first, and see how many of them you can spend, and then work backwards, right? And with each step, we want to have basically a current sum or current amount, and then, you know, see how much we can subtract at once, perform the subtraction, update that current amount, and then restart that process of work from highest to lowest. See how much we can subtract that amount, right, until we get down to zero. And really, that's what we did here. As long as this number is greater than zero, subtract from the current amount. And what this does is it goes through those denominations, okay, from highest to lowest, so long as, right, where this denomination is less than or equal to that current number, we subtract from it, return that new current number, and then here's the only like trick, right, where instead of actually appending in the coin that we spent, we append in like the equivalent Roman numeral by making sure the indices align, and then appending that corresponding Roman numeral because of it, right? So, we just use the subtract from, spit out the new current number and the Roman numeral we used to get there, and then add that to the list, and then finally join it together. And then, we remember that it just didn't work. We have this new trick about the preceding numbers. So our easiest fix was just, okay, well, when we get to something like the number 9 or whatever, make a new corresponding value that corresponds to 9. It says, well, 9 is actually Ix, nothing fancy. And remember, the pitfall I ran into was trying to make it fancy and trying to like employ more logic than I needed to at first. And like I said, that ended up taking me an hour to go down that route, right? Whereas this would have been a lot easier. So just do the easy thing first is my recommendation. If it looks fairly easy, do that. If you run into a problem with it, with the easy solution, then you can always make it harder, right? Do something a little bit more complicated. The harder solution was kind of like employed this trick of seeing, okay, if we perform the subtraction and we get down to say the number is 4, the current number is 4, and our denomination is 5, right? Instead of just using this, okay, we can only spend the coin if it's less than or equal. If it's less than or equal, if we hit, if actually we're greater, if our coin is greater, and that means that we get a 5 minus 4 gives us this difference of -1, right? We're basically using too large of a coin. That's okay, so long as we're in these special cases, right? As long as that difference is -1, -10, or -100, what we can do is spit out the corresponding difference, right? So if it's 1, spit out the I. If it's 9, also spit out the I. If it's 100, if the remainder is, if the remainder is 1, if the difference is 1, spit out the I. If the difference is 10, right, because we have a value of, say, 90, then we want to append an initial x with it, right? And then we want to keep going, essentially, right? So if this number is, say, 90, right, we want to first spit out the x and then keep going with our normal steps, but we want to do that as if we had 100 left, right? Like, that's kind of the trick, is so I just add 10. I say, okay, well, now my current number, to get to 90, let's use this rule of we actually went too far with, if I just use a C, but I can accommodate that by first spitting out that corresponding difference, right, of the x, and then incrementing my current number by that coin, by the value of that difference, and then keep going. That's generally the trick. This becomes a little more, I think it becomes actually like hard to explain maybe how it becomes complicated. If you take a number like 94, the difference, if you look at the coin we're trying to spend, ideally it would be this CX thing. But really the difference is not 100 minus 94. The difference is not 10, right? The difference is 6. So really the way to start thinking about it is 94 equates to 90, comma 4. And then you ask one by one, can I employ the small change problem with that, special case of this thing, right? Can I apply to this? And so you go through and say, okay, for this guy, yeah, we can, we have that special case, right? And we get down to 0, and so we're done. And then for this guy, we also have that special case, get down, append the I, increment it, get up to 5, then subtract that, and we'll be done with that. So it is complicated, right? It's hard to, I don't want to, I feel like at this point it might be easier just to do the reading than have me go through the ins and outs of it. But hopefully that gave you a couple of, those are the big moves, right? It's first just start with a small change where we subtract until we get down to 0 using the biggest coins first, right? And then what we did was kind of employ this trick for our second technique where we say, okay, if we go too far, we're allowed to, in certain circumstances, use that larger coin, right? If we have 5, we can use that 5 as long as first we spit out that difference of the I, right? IV, right? First the I, spit that out, and then we can just increment the number back to be that number 5, and then proceed on. So anyway, the reading maybe will do a better job than I did, but those are the big moves that the reading will take you through. All right. Cool. Let's talk about indices and move on to that. I think I am in my notes. I hope I am. Okay, I am. Beautiful. All right. So I'm sure you all have seen indices in Postgres, or at least heard of them. Generally, the idea with indices is they will allow us to speed up our queries. Specifically, they can allow us to speed up where clauses, right? And also orders, like order by, in certain, if the right kind of index is used. So if you just think about how a where clause works, right? How must it work? If we want to select all the books where the genre equals mystery, then the only way I know, unless we kind of do this index thing, is it's a list, right? SQL is just going to go one by one through each row until it finds the match. When it finds the match, it will store that in memory somewhere. When it gets to the very end of the table, right, then it returns to you all the results. The problem with this is our tables are very big, right? So actually, just even though this is a cost of n, right? If our table is really large, then n can be really large, and it can take a while to do this. And especially if we, an analytics database, our amount of data can be significantly large. In a OLTP database where we're consumer facing, well, then we might care about having performant queries. In general, normally, lots of times it is making the SQL call in a web application is one of the more costly things that you can do. So being efficient with it is a good thing to be aware of. This going one by one, right, looking for all the matches of mystery, this is called a sequential scan. Okay, if you I don't know if I show it somewhere. Yeah, you can see it. If you you can see it in Postgres, what it ends up doing. If you do precede the words explain, analyze to your query, it will tell you what it, like the technique it used. And it was, if you don't have an index, it will say it's performing a sequential scan, meaning it's going one by one by one through each of the rows looking for a match. All right. So how do we speed this up? Well, because we just talked about lists versus dictionaries, right? The general idea is use a dictionary, right? So before, and that's what an index effectively is. So, in other words, before, instead of storing our data like this, we can still store it here, right? We can still store it as a table with these rows, but we're also now going to store this other dictionary. This is our index, right? Where what we'll do is we'll say, okay, we oftentimes make this query of select all from books where the genre equals a certain value, right? We want to search by genre. So what we'll do is we'll indicate what are the IDs that have all the mystery genres, right? Mystery will be our key and the IDs will be our values. And then we'll do the same thing with adventure. Okay, adventure will be our key, and the corresponding IDs here will be our values. And that way, Postgres will know exactly where to look, exactly which IDs to go for. Instead of going one by one, we just go through those that are stored in the list. All right. So it goes, oh, you look for adventure. It retrieves it. It says, okay, adventure, pass it to a hashing function. The hash spits us out these values. And then it turns out, by default, Postgres will automatically hash your primary key. So if you then look for, the rows with the ID 1, it doesn't have to go through all the rows here either. It's just using another index to say exactly where this row is located. And it returns that. Okay? So the whole idea of indexing, at least at this stage, is we're going from searching in data for a list, right, through one by one, to searching for data stored in a dictionary. Yes? Okay. What's the problem with indexes? Like, why don't we just index everything? Well, okay. That was always my question. The answer is, while there is no cost actually to indexing everything with the query itself. The problem is, especially for, say, like a transactional database, right, like a user-facing application. Well, we need to, every time we add a new record, right? So let's say we add a new record here. So we'll add another adventure. Well, think about what happens. So the user just fills out a form, submits this, right? Normally, we just do a simple insert into, right, in the database. But this time, not only do we have to do the insert into, but we also have to update this, okay? So we actually have to perform two updates. This would be ID 4. All right? So what does it mean? Yeah, like our where clauses, they speed up. But our insert into and our deletions are slower, because if we delete this record, right, we not only have to delete it here, but we also have to delete it there, right? Okay, and then the more indexes we add, right, the more, for one record, let's say we have 12 different columns, we have to update 12 different indexes, right? Because now this is, what country was it first published in? We have to, we add a new book, Harry Potter, we both have to update the genre, and then we also have to update what country was it published in. So our inserts and deletions start taking more time. That's not a huge deal, right, with analytics databases, because we're generally we're doing that in batches, we're doing it overnight, things like that. We don't care about updates to the database as much. Right? We care about our select statements, but it is a big deal with transactional databases. All right. What else? Okay, the other thing is you can not only apply an index on one column, you can apply an index on multiple columns if you want. So again, if it was like genre and country, and that's a frequent query for you, select all the mystery genres produced in England, or select all the books of mystery. Select all the books by genre. Let's do it that way. Select all the books by genre and country. You can create an index, and as the keys, it would be like adventure US and adventure, right? England. Okay, so that's possible as well. Right, these are all, so you want to basically look at your frequent queries, and that's where you'll add indices. The other thing to know is indices can also be used for ordering our data, right? If you think about ordering the data, say you want to order by price, that's pretty costly, right? Like sorting it, you have to go you'll have to go one by one through all the prices, and keep updating that list, right? As you kind of find your new min, you add it to the front. That can be pretty costly. So to index on price and to make it faster to perform an order by, well, to do that, you can't really use a dictionary anymore. You have to use this thing called a tree. So let's talk a little bit about that. I'm going to do my best here. This is a binary search tree. If you look at the Postgres documentation, it will call it a B tree. All right. So we'll start with the number 10. And let's say these are all prices. All right. So we'll insert the number 10, and I'll zoom in on this. And that goes, this is our root, what's called your root node. Okay. And now we'll insert the number 5. That's pretty good. Yeah, we'll insert the number 5. And the number 5 is less than 10, so it goes to the left. Then we'll insert the number 15. Number 15 is greater than 10, it goes to the right. Let's insert the number 20, and let's see if we can think about what's going to happen. It's going to go look at the root node and say, is 20 greater or less than 10? It's greater, so it goes to the next step. Then it asks the same question. Is 20 greater or less than 15? It's greater, so it should go to this branch to the right here. All right, let's do one more, or we'll do a couple more. We do 25. Again, it asks the same questions. If we do 25, it's all yes, 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 right? Bigger than this guy, bigger than this guy, bigger than this guy. Should go right here. And then we'll do a different one. All right. Now let's do something maybe more interesting. Let's try to place one here. So we need something less than 10, right? So that would be, 1 through 9. And then if we want to place it here, it would have to be bigger than 5. So between 5 and 10. So that would be like 7. Let's do 7. And now if we want to place it here, it would have to be bigger than 10, but less than 5. All right, so let's see what that would be. Bigger than 10, wait, less than 10, sorry, less than 10 is 5, and then also less than 5, so that'd be like 3. Okay, and then, keep going down the list. So let's just do one last one. So so we have 10, less than 10 brings us to 5, and then this is 5, greater than 5 is 7. If we want to go here, greater than 7 would be something like 8, right? So I think that would work here. All right, that's our last insertion. Okay, so this now, why does this help us? This is us like kind of updating the index, right? As new records, as new prices are stored, this crazy tree thing binary search tree is going to be constructed. Let's think about what happens if now we want to look for the value of 8, right? We want to find the value of 8. It knows the path to kind of look at because it says, okay, we want to find 8. So we start with the root node. The root node is 10. We know 8 is less than 10. That means we have to go left, right? Now we find what our next value is, 5. 8 is bigger than 5. We have to go right. 8 is bigger than 7, we have to go right. Okay? Each time we do this, it not always, but if your data is what's called balanced, meaning that like that generally these guys have both have multiple branches, we can reduce our data in half with each step through the tree, right? We can always like once we know that we're going through here, we don't have to think about search through any of this data, right? Once we know we have a value less than 10, we can ignore this. So that's why, you can start, we can talk more about it. I don't think we will, but you can start to see why, like for ordering data or for looking for something, say, between certain values, right? This can be for numeric data. This can be this is the index. This is what will be going on under the hood when you construct an index in Postgres, all right, is a binary search tree, okay? Again, same cost. As we insert data, we'll have to update this thing too. So inserts and deletions take more time, but searching for values of a certain amount, it helps. Between certain amounts, that helps, right? Or ordering the data also helps. That might be it about, last thing. Okay. So you create your index. You want to make sure you use it. When will you not be using it? If I index first name equals Sam, or if I index just the raw data stored, and then I look for this value uppercased, that's not going to work. Like Postgres will automatically ignore the index. Why? Because it's storing a key of lowercase Sam, not a key of uppercase Sam, right? So if you apply a function to the column that after your where clause, it's going to ignore your index. So all that good work you did won't be used. So what should you do? You should uppercase your value. If you're performing this query, great, store it that way. That way you don't have to perform the function here. So that's kind of like a little trick. Same thing for like extract year, right? This is not going to be using your index because it's not storing the data as 2021, right? You should store the year in a separate column if you know that, right, in an analytical database, if you know that you're performing that query a lot, okay? All right, so that's indices, right? And that's, what goes on under the hood. I think I'll let you... Let me see if there's a good way. The other thing to just know about is joins and why they're costly, right? And there's two different joins that the reading goes through. The first is like a nested join, right? Which is like our brute force approach. So if you have, say we, select all from customers, maybe we'll write it out. Select all from customers, join customers, I guess we have a .customer ID equals orders.customer ID. It's going to have to find the match, right, as we know, for all of the values that line up. So what does it do? Starts with the first ID of 1 and then goes through all of the corresponding orders. This is the brute force approach. Finds all the matches. Here's our match. Then what does it do? Go to the next value. 2. Look for all the matches. Go to the next value, 4. Look for all the matches, etc. What's the cost of this? N times by k, right, where n is one column and k is a different column, but it's effectively n squared. Because of that, this strategy is only used by Postgres or SQL if you have a small amount of data, meaning like 10 rows in each column, in each of these tables, okay? Otherwise, it will try to employ a different technique. The go-to one in Postgres is a hash join, which that probably makes sense. So what will it do? It sees the join. Say you join. Here I'm joining on foreign key, on primary key, foreign keys. In Postgres, by default they will be hashed. But let's say you forgot to specify that this was a primary key or that this was a foreign key. What will Postgres do? It will construct the hash of the smaller table first, right? Meaning it will store these values by the ID, right? And that way, and then it will perform a sequential scan. So I show that here. So here, all of the orders, let me make this, downgrade this. Okay, all of the orders with a customer ID of 1 are stored under this key. All of the orders with a customer ID of 4, right, are stored here. All the orders of a customer ID of 6 are stored here. Okay, so this is the first step, hash the smaller table. The second step now is to go through, this is the orders table, right, and we hashed it. Now the second thing is to go just go one by one through the other table and say, okay, here's the ID of 1. Is there a match? But instead of going through the whole list, what do? We just say, orders, customer, I don't even like this name. We just say, orders table, this hashed orders thing, go here. Look at the ID of 1. And then for each of these values, we append in this thing, right? Combine this value with the customer data, combine this information with that same customer data. Then go to the next guy, Bob. Instead of looping through all my orders, just say orders square bracket 2, right? And what do we know happens? With an inner join, it will ignore this. With the outer join, it will still give you Bob, but not have any corresponding order information, right? Then what do we go? Go to the next one. So you still have to go perform a sequential scan on one of the tables, but you don't have to do a nested loop, right? So the cost of this is effectively 2n, right? Because the cost of, or it's really n plus k, or let's say k plus n, because it's the cost of 1 going through this whole table, this is an orders table, going through this whole orders table one by one to construct this dictionary, right? Insert data into this dictionary. So that's our cost of k. And then it's another scan where we go through each of these records and perform a lookup for each one. Okay? So k plus n as opposed to n squared, right? Or you can think of this as like k plus n as opposed to k times n, or just like this is effectively 2n, which reduces down to n, right? So this is how it works under the hood. So why is this thing such bad news? Like, why do we care? If it's efficient, and this is what Postgres does, what's the problem here? The problem is storing this dictionary. This dictionary can get quite large, and so constructing these hashed values, can take some time. And then 2, it can get so large that instead of storing it in memory, we have to write it to disk. And that's really when things can get costly, because reading and writing from disk is a lot longer than reading and writing from memory, to memory. Okay? So with a large table and you're constructing this hash, and now Postgres has to write to disk to save memory space, this can end up taking a long time. And if you do the explain analyze, you'll see that these things can take, this is half a second, right? It can take a good amount of time. And this is not a lot of data at all, right? So, yeah, being concerned with joins, like what can you do about this? Basically, the answer is, join less. Only join on data that you need. All right, so let's just go into that. How do you do that? Only join on tables that are necessary. If you don't have to join, 3 tables, don't. And you'll see that mistake just all the time. The second thing is reduce the data as much as possible before performing the join. So, example of that is maybe you do your where clause first, right? Select all, select all products if we only care about watches, where the product name is watch, and then join on that subset of the data, right? Because now we only have to hash a subset of the data instead of the entire table. Other things that reduce our data are group bys. So perform the group bys first, right? To reduce the data. I have a lab where you'll have to go through these steps. And then obviously this, right? If you index the column, right? If we have already indexed our data, we won't have to index it on the join, right? So this is why by default Postgres will, if you, as long as you specify that this is a primary key and this is a foreign key, it will already have indexed that for you. And then the other things is join on integer values. Try to, if it's not indexed, try to join on an integer value as opposed to like a string. If you think about reading a string, that means reading all the text and making sure all that text lines up. That's pretty costly. And then, outer joins, don't like not use an outer join and then get the wrong answer, right? Outer joins give you a different result, as you know, than an inner join. Just know that they are more costly. So if you don't need an outer join, don't use it, because what does an outer join do? It returns the data, including the rows that don't have a corresponding ID. It will still return that entire table, and so returning more data costs more than returning less data, right? Inner joins only return the data where there's a match of the primary key and foreign key. Okay, so generally the tips are to reduce the data before performing the join. That's the advice. All right, and only join tables that need to be joined. Questions about this? I'm not the best at this stuff, but hope maybe I'll be able to answer your questions. Go for it.
I was just wondering, is there a trade-off between optimizing reading versus optimizing writing
I
to a
think
table?
I think so. Writing to a table. Oh, okay, so performing select statements. Well, we saw it. We saw it with indices, right? That's the thing that most comes up in my mind, is right as that is the trade-off. Is we now not only have to update one thing, just a new row, but with every index, we have to update the index itself as well, right?
So it's like basically anytime, I guess you have a situation where you don't need to update a table too much, like hashing for everything probably doesn't have a cost. But if you do have to update the table kind of consistently, then you run into some trouble. Is that
Yeah,
what it is?
exactly. So where can you like kind of index without, worry, is like analytics databases actually. Like I think a lot of them, I'd have to look it up, but I like Snowflake, for example, essentially performs it. They do this micro partitioning thing. They are essentially like performing an index on every column, I think. I'm pretty sure close a lot of them. So analytics
I,
databases, go ahead.
Sorry, I was visualizing the micropartitions as basically like an index of an index, right? Because they're kind of like indexing twice in a way, or is
Maybe.
that
Well, I'd have to re-look at it to give you a great answer about that. But yeah, the point is like analytics databases essentially are trying to do this. Why? Because in general, when you're analytics databases having all the data in your database, like creating all that data, inserting all those records, that can happen overnight lots of times, right? And then we can perform uh, our our analytical queries on them. So we don't really care so much with analytics databases about inserting, removing our data. Where do we care? Twitter, or like Facebook, right? When you post something to Facebook, well, yeah, waiting half a second, or you search something on Google, or really any consumer-facing application. Now I have to update 10 different things just to create a Twitter post. Like that's costly. Okay, so that's kind of like the easy split here. You can see. Um, yeah. Other question. Hopefully, you understand why joins are costly. Uh, the right storing this dictionary. There's or doing the nested loop. I also put in a reference, and if you look at the resources, this shows another strategy for a join called like this hash match. No, it's in your reading. Is a separate strategy called the sort and merge join. Um, you might want to look at that. We will probably go through it at a certain point. It's another strategy that can be performed. I think it's worth knowing about. So just look at his reading. I thought he was doing a good job, so I put it in there. And then you saw how to optimize, right? Optimize means just join less data. That's basically the advice. All right, be aware of it.
Jeff, do you know of any way to speed up a geospatial join?
No, I mean what I'm thinking is like the database underneath might might be what you want to do. So this like geospatial. Let's say you want to select things in a certain region. Okay. Well, this is kind of similar to now in ML, like in like with LLMs, you see this a lot with like search engines, right? Where I want to find a document that talks about I store a bunch of data, a bunch of text data. Have a bunch of articles, and now I'm building a search engine and tell me everything about World War One. Okay, so what you want to do is find the document that comes closest, right? And same thing here. Find the document that comes closest. So these are vector databases. So you can look up like vector databases. And that might be like closer to the answer. And the idea is that it can serve. I don't really remember exactly how it does this, but it essentially takes your thing World War One, hashes that or translates that into a certain like topic value, and then takes the text here, and then that's also turns into a similar like topic value, and then it can search and see what's closest here versus here. That it's probably way. Maybe what I said was 70% accurate. I hope, but anyway, vector databases is, in my view, doing something similar. So you can look at like vector databases. The most popular one that I think is like Pinecone. But those are kind of an interesting thing to look at, and then they're employing really what they're employing is something called nearest neighbors, which is just a little hard to explain right now. But this is what I would look at. All right.
So Jeff, so you mentioned like creating like index. One is like using like a dictionary kind of.
Mm-hmm.
Another is like binary search tree, like how they how they like decide which one,
I
or
think you can
like
specify it in Postgres. I linked to the Postgres documentation here, and I also linked to that relevant type. I wonder if well, it says actually which column. Let's go multi-column indexes. Let's do this. The indices in order by. I wonder if you can. My guess is there's a way to specify whether or not you want to use like a B tree,
mm.
or use like a hashed index. But
So like hash, the complexity is like order of one, right?
Mm-hmm.
But the B tree like probably a log n or something like
Yeah,
so.
exactly. It's
The,
log n. It's log n, I
so
believe.
definitely worse, right? So
Yeah, but
why
not.
choose B tree?
Well, okay. Why would you use a B tree? Sorting data, right? Like sorting data with a hash. How do I can. It's good with like exact matches of like a string, but something like more or less than the data is not sorted in the dictionary, whereas here it is, right? It has some order. That's the idea.
And then is it automatically like do some like trimming or some
Yeah,
like
will it balance the tree?
balance? Yeah.
Yeah, it will rebalance. Like most databases will rebalance the tree. Meaning you see you get for those of you who don't know, you can see how this data is like not balanced, right? We have all this over here. That's generally not great because we're not over here. We're cutting off this whole branch, all right, which is great. Like if I look over here, but as I go down here and proceed down, I'm not really cutting out. There could be a lot of data, I'd have to still look through. I'm not really cutting out any data. I'm cutting out all this stuff, but I didn't really gain too much in terms of eliminating my data as I go from here to here, as opposed to if I had evenly branched stuff, with each step, I'm removing a good amount of data, right? If you can imagine this tree, like this whole thing could be an enormous branch, right? That just by moving one step, I'm eliminating a big portion, right? So unbalanced trees, you're losing the benefit of these optimized kind of search for values. By the way, you can search, if you want to learn more about trees or binary search trees, you can look on YouTube. I think probably my guess is CS50. You can look at binary search or binary search trees, and it might be able to get a good answer there. All right, so those were good questions. I'm going to let you all work through these problems. So certainly indices, do the reading and joins. This is fun. I have you implement the hash join.